Hi, it's been a while, actually more than a month, since the last recording. I was unable to solve problem 15. Then I started on problem 16, which turned out to be technical, and I just wasn't able to find the right idea. And I realized then that I lacked the motivation. I believe that I had a moral breakdown, really. So I went back to studying algebraic curves. I thought I had some fundamental uncertainties or misunderstandings, and I think it turned out to be both. So I took this book, which I've shown to you before, by Cohn, and read the chapter on Dedekind domains and extensions of them. And then I wanted to make some examples of curves, and particularly investigating the maximal ideals, or since it was Dedekind domains, then the prime ideals. I started working on the circle, and that's an example they also use in the book, and I could do that. And then I wanted to work on another curve, namely this curve, y to the third plus xy plus x squared vanishes. I've drawn it here, and it's a third order curve that's not an elliptic curve, because we have a singular point here with self-intersection. So I wanted to look in this functional space, what are the maximal ideals? What do they look like? And the first point is to be able to factorize a domain like x equal to minus, or x minus x plus 0.1, which should split to three ideals. I took an example 4.-2 and then the imaginary points, or complex points rather, and tried to compute the product of these three ideals, and it turned out to give exactly x minus 4. So I started with these two, the product of these two, and could reduce it to this. And then multiplying it by that, I finally found out that it was generated exactly by x plus 4. It should be x minus 4. So I made some mistakes here in what I wrote, but never mind. Then I took the double point. That is x equals minus 2/9. That gives this double point here. Oh, it's not a double point, it's a vertical tangent. So here, this ideal should ramify. Now, the first thing following the book is to see, we work in the polynomial ring C with squared x, and then we no, that's not it. We take this ideal in the polynomial ring, and that's a uniformizer in the polynomial field, the field of rational functions. And then we make the completion with respect to that. So that's all series in x plus 4/24, infinite series, with coefficients in the that will actually then be complex numbers. That's the completion. Then we tensor the functional field, that is C of x extended with, that's what I wrote up here. This is our functional field. Tensor it with the completion, and that is just equal to enlarging the constants. And we should find a solution to this equation in kV, in the completion. And I could find one and only one, and that means that we can write it as, we can factor this to K1, that's containing this solution, and then it must be one extended with a square root, 1 of order 2 over kV. And that indicates that we have this factorization, and I could compute that pretty easy. So x is defined and y, so all the polynomials generated by these two, or these two. And this turns out to be right. I could do that like I did the first one. All right, so far. Now came the thing that I really didn't understand, how to factorize this polynomial. And I thought that they would factor into these two ideals. So I tried this one squared times that one, this one squared times that one, to see if we had any luck. I did the same thing, of course, first, or then I did the same thing, finding a solution in kV where it's now series in x. And I did find one solution, and only one, so it's the same again. It must be some x must factor with 1, and then an ideal, a maximal ideal squared. All this is according to the theory of Dedekind domains. And I really believed that this would be a Dedekind domain. Well, I was wrong. It turned out that x divided by y was an integral function, and I'll just show you. Now what have we got here? That's the next, yeah. So here we have the solutions, we call the three solutions in some algebraic extension for I1, I2, I3. Then we have the trace of the y's vanish, the coefficient to y squared. So that's sigma 1 of the y's is naught. Sigma 2 being y1, y2, y1, y3 plus y2, y3. The symmetric polynomials equals x. And the third symmetric one, which is y1 times y2 times y3, then equals minus x squared. So now we do the same thing with x divided by y. We put them on common denominator. So here we get y2, y3, y1, y3, and y1, y2 from this guy. And this turns out to be, that was exactly x, x times x, y2, y1, that's minus x squared. So that turned out to be minus unity. You can see where this is going by now, I believe. We have to square this guy because we get all of them twice. There we go. And then they must be squared here. So we have... No, now that's silly. What on earth am I doing? So the common denominator is x1, x2, x3, so we have to extend this with y3, this with y2, and this with y1, so that's what it gives. And then the sum of the guys vanish, so this just vanishes. And that was minus x squared, so that gives minus x. That means that we have a polynomial t to the third. Sigma 1 was minus 1. This vanishes, and then plus x. So this is the equation for x divided by y. And the coefficients are all polynomials in x, so that means that this is an integral function. I also discovered that y squared divided by x was, but actually it turns out that they are connected. As you can see here, the sum of them gives minus 1. And it just comes from the equation. You divide the equation here by what? By xy. So y squared divided by x plus 1 plus x divided by y vanishes. So we take the ideal generated by y squared x and x divided by y. Oh, before going to the ideal, we should find out what are the ring of integral functions. And I wrote that here. It turns out that this is the ring of integral functions. We should be able to see that without working on it for 14 days. So I wondered what we could do. And when we take x minus 4, which we can then split into 3 ideals, and we can do that because in general we'll have 3 solutions to this equation, and x equals something. It's a third degree equation. So that means that x minus something must have degree 3. On the other hand, y plus something or minus something, well, we'll generally have 2 solutions. So that means that y must be of degree 2. And that's of course in the functional ring CFX extended with y. So we get this in CFX we have the place at infinity. And the valuation of a polynomial is minus the degree of the polynomial. And if it's an arbitrary fraction, then it's the degree of the denominator minus the degree of the numerator. So that's this degree of a polynomial. And when we extend it, then we get a new one where x does not have degree 1, but degree 3 and y degree 2. So can we make some positive guys from this? And it appears that we can make, if we take x minus a divided by y, or any guy, y by plus c, the degree of this guy is unity, 3 minus 2. So this should be an integral function. That's another way of looking at the ideals. I think that's the right way to look at the ideals, and not the way I wrote them here as having two, because this way they do not come as principal ideals. And I think it's a principal ideal domain. I think this guy is a principal ideal domain. I haven't done the details though, but I believe now that the principal ideals all have this form. Now, what do we do? So this has to be written. I don't think we can generate x by just saying y squared divided by x, then multiplying by these guys. But actually multiplying these two gives y. So that's a factorization of the ideal generated by y. And squaring this one and multiplying it by this gives x. And that means that, we have written it here, that a squared times b actually gives x. So I managed finally to factorize the ideal x. But the point was that this was the ring of integral functions, not the one I expected first. That was a great surprise, and that means that this is a Dedekind domain, and the one I expected is not. So that was what I learned. And then I tried to move on in the book. That I read some sections in the theory of function spaces, and I realized there that I simply didn't know how to find the maximal ideals of the function spaces. So I hope now that I have a way of doing that. And they should all be generated by a guy of this form. Of course, not all generate Or do they? Maybe they do, I don't know. So that was the great surprise. Of course, x divided by y, oops, y squared, that is 4. So I made a mistake here. We need they must be of this point, this form. And of course, y squared divided by x was minus 1 minus x divided by y. Doesn't it have that form? No, it doesn't. So this is not the general form, really. So it seems it can be plus c. That. So now we have x divided by y, ab being naught, and then adding unity, and then we get this ideal. So that seems to be the general form of the ideals, of the of the maximal ideals, which of course is also the prime ideals in a Dedekind domain. So, while I was doing all that work, I think I found out how to solve problem 15. By the way, we have the field, the base field. There's a finite field where Q is a prime power. Then we have a K polynomials in N independent N variables. And then we have a point where A lies in algebraic extensions of K, and they generate an algebraic extension L. That must, of course, being an extension of K, being some field Q to Lth. The problem was that I should prove that it had L solutions, that the equations f1 to fk has L solutions in this space, or Q to L solutions, and I wasn't able to do that. I think I can do that now, so let's take a look at it. My idea is that we make a prime factorization of L and then we take the primes one at a time. First, P1 to I1. One of these A's must be in an extension with this P1 to I1. If they all were in some smaller extensions, then the total extension would be in that smaller extension. So one of them have to be in a field with Pi1. So let's call that one A1. That's a finite field, and that means that it is FQ, that was P1 to I1 times P2 to some power, which is smaller than or equal to I2, etc. PM to JM. So they are all smaller or equal to I2. So if we go to the first, that is smaller. Let's say that's J2 is smaller than I2. Then A2 must lie in an extension of L1. And since it's a finite field, it must be the power to Q, there should be a Q of course, is higher, or is a multiplum of this guy. And since it only contains these primes, we must of course have P2 to I2, and the other ones will be at least as great. You see the idea that we get a number of extensions. The minimal polynomial of A1 has coefficients in K. The minimal polynomial of A2 has coefficients in here, and they can all be expressed by A1. So that means we have a polynomial P K of x giving A1, and A2, there we have a polynomial with coefficients in K of x, y. You see the idea now that in a finite number of steps we will have polynomials, a series of polynomials whose solutions generate L, and the degrees, we know the degrees, and the product of all those degrees are L. Should call them P1, P2. So we don't know. We get one for each. Of course, the last ones will probably be linear when we already have found the space. So they'll just be of the form, say, xn is given by some polynomial defined by the rest of the coefficient or rest of the independence here. And that also tells us the number of solutions, because here we have degree of P1 solutions in the finite field. Here we have degree P2 in the extension, so the product is the solutions satisfying the, I don't know, we have to take them all because they must satisfy all the solutions. Of course, we don't know in which sequence they are chosen. So that way these polynomials, they define a maximal ideal. All right, they define an ideal, and the splitting field is exactly L. And that means that the well, and the product of the idea, the degrees, is exactly q to lth. Or what? You just have to think about this. The degree of this it's p to some power. So that means the degree is my God. So this is the degree of 1. So the product of all the degrees give exactly, what was it called? Q to lth, give exactly L. And that's the norm of the maximal ideal as well. And it's a number of points. Here I'm using problem 14, I think. So that's as far as it gets with the solution of problem 15. I believe that together with the first video, this should be all that is needed. And now I've gotten it off my chest. And along the way, I think I got the idea on how to make the next problem. So it does require a technicality, but one should be able to find it, of course. It was very interesting to experience this, but I wasn't able to get the idea. There's a finite number of ideas one can try. It was just a question of trying them, and I didn't have the heart to go through them. I got confused by the complexity of the problem. I wasn't able to simplify it. So that's a moral breakdown, and being able to realize that one needs to study more to be able to do something, that's very important. So don't give up. You have maybe a misunderstanding, maybe there's just lack of knowledge, and it sits in the back of your head and makes it impossible to use your full potential. Or I don't know what the full potential means, but then your normal potential at least. All right, so that was a report on a moral breakdown and how I cope with it.